What I want to tell you about tonight is not everything that's happening in astronomy and astrophysics, because that would just be too much. It would be more like a little snack platter of various tidbits. Instead, I want to give you a whole entree, something really meaty and juicy, and focus just on one of the most important topics in contemporary astronomy, which is the search for habitable worlds. And I think one has to really realize that this is a very new subject. It was only back in 1996, you can't quite see it because it's cropped, but this is a Time magazine cover from 1996. That was the first time when we have the first reproducible evidence for planets outside of the solar system. 15 years is a very short period of time in the history of astronomy, of course. It was just 400 years ago that Galileo used the first telescope to find the Galilean satellites of Jupiter. So 15 years is just a blink in the eye, although if you look at that political banner upper left, it looks like it was quite a long time ago. Indeed, possibly in another galaxy altogether. But in those short 15 years, we've made a lot of progress in the search for planets outside of our solar system. Just to give you a setting for the feeling for what's been discovered, here's the next slide, which shows you discovery space, which basically shows you the mass of the planet over here in units of the of an Earth mass here. So here's one Earth mass right here, and also showing you how far away the planets are from their central star in orbits, in units of 1 AU, 1 astronomical unit, which is the Earth's sun distance. So Earth is out here at 1, Jupiter's out at 5.2, Saturn's around 10 or so, Uranus and Neptune are farther out as well. So what you see here is that as of roughly the end of 2010, there had been over 500 planets found outside the solar system. 15 years ago we had 0, now we have over 500, and I'm going to show you about another new 1,000 towards the end of this talk. And a lot of these planets have been found primarily up in this regime of the discovery space because that's where the observational bias is. It's easier to find massive objects. It's easier to find objects on short period orbits close to their star because most of these, maybe 450 or so of these, have been found by a particular technique called Doppler spectroscopy, where you don't see the planet directly, but you infer the planet's existence by watching the star wobble around the center of mass of the star-planet system. And a planet like our Jupiter makes our sun wobble back and forth by plus or minus 30 miles per hour. So you can measure a star moving in space back and forth by 30 miles per hour. You can say, hey, that must have a Jupiter mass object around it. So most of those have been found by Doppler spectroscopy. A few have been found by direct imaging, one by Hubble and a couple by ground-based telescopes out here at these rather wide distances where you can actually see the planet and distinguish it from the star. And a couple have been found by microlensing in here. And just to give you a general feeling for what's been found, a lot of them are what you might call cold Jupiters, sort of like our own Jupiter. They're out at distances where they're pretty much maybe having temperatures of a few hundred degrees Kelvin, like Jupiter's surface does. But most of them that are in close are these so-called hot Jupiters, which are actually the very first one found by Michel Mayor and Didier Queloz in '95 was a hot Jupiter right around here. They're in very close. They're a very high temperature result. Not a place where you want to own real estate, but they're still interesting. And there are a few intermediate ones, and perhaps most intriguingly, we're beginning to find planets down here with masses similar to Uranus and Neptune. These are the so-called super-Earths. Some of them are, again, rather hot super-Earths. Some of them are kind of cold, ones found by microlensing. But we've yet to find one right in this little magic regime here, the so-called habitable zone, where around a sun-like star, at least, an Earth-mass planet is likely to have an atmosphere which is supportive of having liquid water. That's the eventual goal of this field, is trying to find not just planets for their own purposes, although that's interesting enough, but we actually really want to find eventually habitable worlds. Now, another aspect of this diagram is that a good number of these planets found in here have been found by a technique called transiting, where you actually detect the presence of the planet by having the planet pass in front of a star and make the star's light dim by just a tiny amount. And the ones that have been found so far, these so-called hot Jupiters, are kind of big and puffy. They block about 1% of the star's light. You can measure that from the ground. But if you want to find a habitable Earth, you have a much harder task. Here's an image of Venus passing in front of the sun back in 2004, taken by an amateur astronomer from Northern Virginia. The key thing is that Earth is the same size as Venus, of course. And so an Earth is roughly 100 times smaller in size than the sun. That means the fractional area that it blocks is 10,000 times smaller. That means if you want to actually detect that dimming of the star by the planet passing in front, you better be able to measure the light of the star maybe a part in 10 to the 5. You can't do that sort of measurement from the ground. There's just too much atmospheric distortion by looking at stars from underneath our atmosphere. In order to make that sort of very precise measurement of how bright a star is and seeing a little part in 10 to the 5 or 10 to the 4 dip, you have to go to space. That has now been done, amazingly enough. Back in March of 2009, just a little over 2 years ago, NASA launched the Kepler spacecraft mission. This is a telescope designed to do nothing but stare at stars and trying to find planets. It's a rather modest-sized telescope in some sense. This is a 1.4 meter diameter primary mirror back here with a 95 centimeter Schmidt corrector on the front. The key thing is that it has a 95 megapixel camera. It's the world's biggest digital camera in space. And it just sits there staring, hoping to find the dimming of a star's light due to having a planet pass in front. And the way it's doing it is by staring at the same patch of sky in the constellations Cygnus and Lyra. Here's the Milky Way up and down here. And here's the Kepler field of view. It's basically 10 degrees on the side, 100 square degrees of sky. And it's following the brightnesses of about 150,000 stars continuously. Kepler has no moving parts. It did have a sunshade, which is on top of it. But once it was taken up into orbit and commissioned, making sure it was work, they blew the sun shield off with explosive bolts. And then Kepler cannot close its eye. It just stares at this field of view the entire time. It's sort of like Malcolm McDowell in Clockwork Orange, if any of you have seen that movie where he has his eyelids propped up. That's kind of the rather gory image I have of poor Kepler up there staring. And so it's been staring now for almost 2 years. It began actually just a little over 2 years. On May 2nd, 2009, it began science operations. And Kepler is now beginning to turn its harvest of results. And one of the first hot new results that's come out is the discovery of its first rocky planet, cleverly named Kepler 10b. This is how astronomers name objects like this. The Kepler 10 is basically the star, and B is the planet's name. We don't get anything more exotic than that. We don't name them after scientists. We just call them B. Next one will be C, next one D, and so on until you run on the alphabet. The exciting thing about this is that it is for sure a rocky planet, because when you have a size of the planet and the size of the star, you know what the radius of the planet is. If you have also a mass for the planet, which we happen to have in this case, because this particular host star, the Kepler 10 star, is a G-type star like our sun. It's a fairly old star, maybe 12 billion years old. It's a nice stable star. We actually were able to get a Doppler measurement of what the mass of the planet. We were actually able to measure the wobble of that star around the center of mass and get the mass. And when you have both the radius and the mass, then you can get a density. And this thing is dense, 8.8 grams per cubic centimeter. For reference, the Earth's density is about 5.5 grams per cubic centimeter. This is what you would get if you took something as this more or less the same density of Earth or a little bit denser and crank it up by about a factor of 4.5 in mass. That's the sort of density you get. This is not, however, again, a place where you want to buy real estate, because it's in very close. It orbits its star every less than a day, 0.84 days, which means it's a very hot world. The artist who made this image basically imagined this as being a world which is a living volcano. It's just like a kiloway lava flow over the entire planet. To put that in perspective with what else has been found recently, here's the result for Kepler 10b on a plot showing you the radius of the planet versus the mass, with Earth and Venus sitting here with basically one Earth mass and one Earth radius, or pretty close to it. And here's Kepler 10b. It's got a very nice tight error bar because the Kepler photometry is so precise, and because the Doppler velocity precision was so good. There's a competing, possibly rocky planet found by a French satellite called Corot, which was announced a few years earlier. Fortunately, their star is pretty a noisy star, so they don't have a good mass from it, from the Doppler spectroscopy, so they have a rather big error bar in what the mass is, and their photometry is not so good either. It's about roughly a telescope 1/3 as big as Kepler. And so it's unclear if that's the first, for sure, rocky world or if Kepler 10b is, but there's a good chance maybe both of them are. So this is telling us that we are indeed now able to find rocky planets on other stars. But the real biggest part of the harvest from Kepler was just announced a couple of months ago in February, when Kepler made its so-called second data release. The Kepler data, of course, are owned by the public, by NASA, and so after the Kepler folks digest the data a little bit, it's all released to the public, let them know what's been found. And this first big data release, they actually show that they now have not 500 planetary candidates, but over 1,200. Now, some of these probably are going to be false positives. There's a lot of ways to be fooled. If you happen to have a background binary star that's lined up with the star you're looking at in the foreground, that binary star is changing its light curve, you can be fooled into thinking that really is a planet in front of the foreground star. You can't always rule those out. So the statistics that the Kepler teams have done so far show that maybe 80, 90% of their candidates are correct, maybe 10 or 20% are false. So of those 1,200, I would say probably a good 1,000 of those are the right ones. Unfortunately, we don't know which ones are the right ones, but for statistics, that's okay. We just know that pretty much this is what's been found, roughly 1,000 planet candidates. And they break down into very different sizes. A fair number of them are Jupiter size, a lot of them are Neptune size, smaller and smaller sizes, 288 super-Earth, and even 68 that are Earth size. And of course, as you go to smaller and smaller sizes, it gets getting harder and harder to see. So the really big guys, for sure they know they're complete in finding all those. As you get down to Earth size, even super-Earth size, well, there are probably more there that they'll have to work harder and harder to find them. So it's pretty amazing that within this first 2 years of operations, they've already found so many new planets, basically tripling the number of known planets from what was known over the previous 15 years. And I'll show you a bit later on that a good number of them are actually in their habitable zone. Just to show you where those planets fall on that tiling of the Kepler 95 megapixel camera in the sky, the blue dots are the Earths. They're pretty much close to the galactic plane as well as away from it. The super-Earths are distributed everywhere. Same thing with the Neptunes and the gas giants planet. So there's pretty much evidence that wherever you look in our galaxy along the spiral arms, you're going to find these 4 types of planets, which we, of course, believe are basically ice giants, gas giants, and rocky planets much like our Earth, although the latter, of course, remains to be completely proven. And here's perhaps an even more spectacular picture of what's been seen. Now we're showing you the size of the planet, which is all the Kepler can detect, of course, because it can't really get the mass. So we sort of infer that that's related to the mass, versus orbital period, which is sort of the same as distance from the star. And the light purple dots up here are the ones which have been found, the transiting planets which have been found before Kepler was launched, roughly 50 or 60 or so of them. The dark purple, dark bluish ones are the ones which Kepler has found in its first data release, released back in June of 2010. Then the yellows are the ones that were just released in this most recent data release. This is the whole now 1,200 candidates in here. And the really exciting thing is that, of course, they really are very complete up here. As you get down to smaller sized planets, you start getting incomplete, so there are probably a lot more down here than can be seen. As you go to longer orbital periods, there are also probably more planets there that they haven't seen, because you want to see multiple transits, since you have to want to watch for many times that orbital period. And this is only 43 days worth of data. So you get the hint that if you could sort of pull away this obscuration, that there would be a lot more planets as you went down to lower masses, smaller sizes, and longer orbital periods. So Kepler cannot quite say how many Earth-like planets are there, but the indications are there are just going to be a lot of them. The universe makes a lot of these large super-Earth planets, not so many gas giants, but it's making more and more as you get smaller and smaller, which is incredibly encouraging for those of us who are hoping to find a lot of Earth-like planets. Now, to focus on those that are in the habitable zone, here are the Kepler candidates to date, though these are sort of a strange bias because most of the orbits found so far are rather short periods, so they tend to be hot. So these are the planets in orbit around low-mass stars, which have, at short period orbits, they're still kind of cool. So there'll be a lot more planets in the habitable zone once Kepler has been able to take its full 3.5 years of data. But even still, they've been able to find some objects even smaller than the size of Earth, and a good number of them, 54 or so, are in this so-called habitable zone where you can have liquid water. I'm going to go off the record at this point and say something, which is that the Kepler team is being very careful to say, we haven't found any habitable Earths yet, we don't know how many of them there are, although they seem to have from the current statistics, or from the current statistics, at least 34% of stars have planets of some sort. A couple of brave souls have taken the Kepler data and extrapolated it well beyond where one can be certain, and claimed that, well, it turns out that we think that maybe, in one case, roughly half of all solar-type stars have a Earth-like planet, namely roughly Earth mass in the habitable zone. That's unproven, that's merely an extrapolation, but if it turns out to be true, that means that roughly half of the stars in the sky when you look up have a habitable world about it. Half the stars in the sky when you look up have a habitable world. I don't know how many times I can say it over and over again. That is just stunning. We don't know if it's true yet, but that's the early indication. So at that point, I think we'll leave you with that thought. And if you want to know more about the history of the search for extrasolar planets, you can look at a book that I've written. But let me also mention that one of the key things that Kepler's frequency of Earth-like planets will be useful for is planning the next steps for how to actually learn more about habitable worlds. NASA is in the process of trying to figure out how to best design a space telescope that will do the search. The Kepler habitable worlds are off towards that Cygnus Lyra area. They tend not to be very close to us. We want to find the closest habitable worlds, and we have to build a very specialized space telescope to do that. There are two concepts that are underway right now that NASA is working on. One is the so-called internal coronagraph, where you try to see the planet by blocking the starlight, so you can, because the star is much brighter than the planet. One concept is the so-called terrestrial planet finder. It's been around for quite some time. This would be basically a 3.5 by 8 meter telescope. Unfortunately, it costs about $6 billion, and so we can't build that. The other concept is called an external occulter, where you take an existing space telescope, like maybe even James Webb Space Telescope once it gets launched, and you fly a very exotic star shield in front of it and use that star shield to block the starlight to allow you to see the planets. We don't quite know exactly which way will be chosen, but NASA hopes to do a downselect between these two concepts in the next couple of years, and maybe 20 years from now we'll actually be flying one of these and being able to take pictures of those planets. So once again, if you want to know more about this, shamelessly, here's a cover of my book, and that's it. Thank you, Alan.